I have a chiral and antichiral. Right, so very good. So this is, so I was going to come to this right now. So this looks like a degeneracy, right? However, I don't have any protection, I haven't imposed any time reversal on the system, right? In fact, I know the system is not time reversal invariant because on one edge, I just have things moving in this direction. And time reversal is local. So if I add a time reversal on one edge, I should have an antichiral one on the same edge. Here, the antichiral one is on the other edge. So what makes it not do this, for example? Okay? Once I open a gap of, this is finite, the difference between levels here is 2 pi over nx, right? So this is gapless, it's a metal. So this is, once I open a finite gap, finites and finites are the same, so I can just tune that gap a little bit more, and I can do this, right? I can do this, I can tune it a little bit more until I have nothing left on the edge. So why doesn't this happen? Well, it doesn't happen because it would require non-local interactions, right? This guy here is localized purely on this edge, and this guy here is localized purely on this edge. So the matrix element between them is exponentially small with e to the minus some gap L over some velocity. So the gap over the length is the bulk gap. So this is the bulk gap. Delta is the bulk gap. Okay? That's the matrix element between them. So if you have finite gap, that matrix element has to go to 0. So there's no coupling between them. In fact, there is coupling, but the coupling is exponentially small. And exponentially small coupling cannot open a gap in systems that are power law, right? These systems are power law in the sense of, 2 pi over nx. Think of this as, the 2D limit where nx and ny both go to infinity in the same, right? The 2D limit would really mean both nx, number of sites in this direction, where I Fourier transformed, and number of sites in this direction go to infinity with an aspect ratio which is constant. So then the levels on one edge are gapless to 2 pi over nx. The coupling between the edges is exponential. You'll never be able to open a gap. Yeah.
Essentially, this is, at least the first part of the story is Lofton's.
This is just Lofton's argument,
Exactly.
right?
But then, in the 80s when they formulated it, I understand the picture was, now, but due to the anomaly, there is one guy popping up on the left side,
Right.
and another guy disappearing on the right side.
Right.
And then you want to write down Jx equals, there's current flow, the whole current. So somehow they want to recombine. And
Well, right. They're not going to be able to recombine because of the matrix elements.
In the 80s, what they said is they have to recombine, and for that reason there has to be an extended state.
In the bulk, yeah. Sure.
So otherwise, how would
Sure.
the electron, how would they recombine with the rise of the point charge?
Well, so in this case here, this doesn't know anything about the extended states because I haven't added. But the way it does know about it doesn't know anything about disorder because I haven't added. But the way it does know about the extended states is the spectral flow. So in other words, if I just because of the Hamiltonian, the k goes to the h of k is h of k plus g. I can just follow this state and go from one end to the other. I certainly can't get this state to flow back into this one. Right?
When you write down, Jx equals something, Uy, Uy is the electromotive, right?
Well, this is, so yes, in this case it's that, but this is supposed to be the generic form of, right? I derived it by, threading flux, but this, right.
Exactly, but what is Jx?
Jx is from here to here through the bulk. Yeah, through the extent. If you were to have like an actual picture, if I was to have an actual picture of this in terms of what happens to the centers of charge, what would happen to the center of charge is the center of charge have the finite states that Ivo was talking about have a flow that looks like this. And these are bulk states. Okay, so they kind of like, so once you take one from here, you just kind of take it through the bulk and put it on the other side. It has to go through the bulk. You're right. Yeah. Right. Okay. Thank you. All right. So this is the quantum Hall effect, but of course, you can understand the quantum Hall effect also from the doubling no-go theorem. So this is Nielsen-Niomia proposed this for 3 dimensions, and we'll get there. But the same thing exists in 2 dimension. Well, I actually don't know if they proposed it only for 3 dimensions. So what they did say is that in a 1D system, you cannot have a chiral mode alone, right? So basically they use some, in 3 dimensions they use some hard Fermi homotopy arguments. But really what it is just, the fact that your Hamiltonian at 0 is equal to a Hamiltonian at 2 pi, so bands have to be continuous. So if you have in pure 1 dimension, not without a chiral mode, you have to have an anti-chiral mode. Okay? So chiral in purely 1D systems, chiral modes come with anti-chiral modes. And you don't even have to have time reversal, so they can look not even like this. They can look, like this. This is 0. This is 2 pi. If I sit here, this is a chiral mode. This is an anti-chiral mode. The point is there have to be regions for every region of positive curve for positive slope has to be a negative slope also. Okay. So when you break the Nielsen-Niomia theorem, so if you violate the Nielsen-Niomia theorem, you can only do it at the surface of a topological insulator. So the surface of a topological insulator, what has done is has taken this chiral mode, moved it on, taken this chiral mode, moved it on that surface, has taken this anti-chiral mode, moved it on this surface, right? So there's a duality between no-go theorems, which we'll talk a lot about, and topological insulators. Every time you have a no-go theorem and you violate it, you're going to end up with a topological. You can only do that at the surface of a topological insulator. Okay, so this is still rather simple, and let's go to more complicated things. So the first thing that I want to do. So, any questions? Yes.
You had one carbon, you said it's not solid for 2
right.
edges, but you did not have to assume that those was gap for that. You didn't have to give respect at all for this argument.
I didn't have to assume that certainly. I mean, if I have, I'm just looking at the time. Certainly, if I had a metal, okay, I could do the same. I could just say the same thing. But the point with a metal is I wouldn't be able to localize a state on one edge. The state would leak, right? The fact that I've got this e to the minus delta L allows me to tell you, if I have a 2D metal, I can't say that something is localized on the edge. Well, it could be an impurity band. But things would happen in the bulk. I just want the bulk to be, my Fermi level in the gap, bulk to not do anything when I insert flux. Okay? Everything would happen on the edges. So that was the purpose of having an insulator. In fact, if you have a bulk, if I have a bulk metal, I couldn't make this argument. The charge, would not be quantized. As Alexander was saying, you could shift things in the Fermi surface of the bulk. They would recombine. They would depend on some time recombination, which would not be universal. Okay, so now let's see what we can do with time reversal. So let's see what's the Nielsen-Niomia, what's the NN theorem with time reversal. Can anybody tell me? So what does it mean in 1 dimension? What would it say in 1 dimension? That you cannot have how many Kramer's points do you have in 1 dimension? 2. So at these 2 Kramer's points, the band structure has to look like this, right? Okay, around here, around the Kramer's point, 0 and 2 pi, or pi, 0 pi. Okay, the Hamiltonian here is what, roughly? What do you think it is? This is k in one dimension. What's the small k Hamiltonian around here, around this point? What is it? Yes, what? How many bands do I have? What's the matrix to describe a two-band Hamiltonian? Pick one. Very good. So you have to have two states for every k, because I can see them. So I have to have a 2 by 2 matrix. That's the Hamiltonian around there. These are called helical modes, right? For every mode that's moving in one direction, I have one moving in the other direction. How many of them do I absolutely need to have in a time reversal invariant lattice? An even number of them, right? Always. Make sense? If I have other ones that are kind of like, you know, I can think of adding some symmetries or having degenerate ones here, for example, or crossings. They'll still come in pairs because of time reversal. Okay, so what does Nielsen-Nioniya theorem tells you with time reversal? You cannot have so odd number of helical modes exist only of the Binghei's topological insulators. Helical modes exist only on the surface of two-dimensional time reversal invariant insulators. Okay? So just by simple picture drawing, we figure out that topological insulators exist. Okay? And we're going to go marching on to higher dimensions, where things become more interesting, and ask, you know, and ask what type of doubling theorems can we have in higher dimensions. And we're mostly interested in things that are isotropic. I like to think of things that, you know, of course I could take a 1D system and just stack it. You know, that would be kind of boring thing to do. I would just stack it and put a small perturbation between them. I could think of that, but that wouldn't be a very interesting thing. Those are anisotropic systems because they have a stacking direction. For example, if I take my quantum Hall state, so now let's go to 2 dimensions. 2 dimensions, and I'm going to try to find semimetals or metals in 2 dimensions. Try to find Nielsen-Nioniya theorems for metals, and then show that the ones that, when you violate them, they're the edge of something. Okay? So, what can I do if I go to 2 dimensions? Well, if I take a chiral edge mode, this is kx, right? That was kx. This is a chiral edge mode. What can I do with just the chiral edge mode in 2 dimensions? Well, I now have ky too. For just 1 second working with periodic boundary conditions in both directions. I can just translate this like this, right? I can just translate it like this, right? For example, how would the Fermi surface look in 2 dimensions if I had kx and ky of a translated chiral mode? How would the Fermi surface look? Well, at ky equals to 0, what's the Fermi surface? 1. What's the Fermi surface of this chiral mode? A point. So let's just draw this point here. Okay? And now I translate it in ky. So I can do this. Okay? Periodic in ky also. This is okay, this is called a 3D quantum Hall effect. This cannot also exist in a 2D system. Why is that? Well, all those modes are chiral. Okay? All those modes are chiral, so I do this mode chiral this mode chiral, this mode chiral, I can manage to put periodic boundary conditions in ky direction, but I still haven't put them in kx. I'm still with the same problem. I can, by translating it in ky, I just stack 1D wires like this, okay, like 1D wires, I stack them together. I can put periodic boundary conditions in the stacking direction, but I'm still, if I have a chiral mode, I'm still stuck with the original problem. So what happens is that this type of chiral mode here, if it's chiral, cannot exist in purely one dimension, in purely two dimensions. Again, is the edge of something, and is the edge of a 3D quantum Hall effect, where I just take this guy here, the 2D quantum Hall effect, my 2D quantum Hall effect, okay, and stack it in the z direction. Now, that's not very interesting because I just stack things, so I don't want to look at that. I could do the same stacking for this topology, for this helical mode that looks like this, okay, for a helical mode that looks like this. But I don't want to do that because now there's a more interesting possibility for the helical mode. Okay? So as I said, in one dimension, if I just have one helical mode, I'm violating Nielsen-Diomia theorem, and this helical mode can appear only at the edge of a 2D topological insulator. So I have the same picture. This is Ny. This is what Binghai was showing, spin up, say spin down with time reversal. Okay? I have another helical mode here. Okay? Why can't this gap open? This gap can't open because of separation in space. This is time reversal symmetry, right? So I have a series of gaps. I have a series of gaps here. So I have one helical mode on this edge, one helical mode on this edge, and I have 4 crossings now. This crossing is at a time reversal invariant momentum. It's Kramer's. It can't open unless you break time reversal. This one is also a time reversal invariant momentum on the other side. Time reversal is local. This can't open. These guys can't open here because they come from different edges. Okay? All right. So, what could I do? What's the Fermi surface? If I put my Fermi level in the bulk gap here, what's the Fermi surface of a helical mode on one edge? 2 points. Okay? Okay, 2 points. So, there's an obvious thing that I can do, which is I can rotate this system, right? I can just take this and go into the higher dimension by just rotating this Fermi surface. So this was called this Kx. This is Kx. This is Ky. Okay? I'm just going to rotate this Fermi surface. Can this Fermi surface exist in a purely two-dimensional system? What do you think? This Fermi surface. Just on one edge, I'm just doing it one Fermi surface. Since physics is local, I could just go on this side and rotate it in a third direction. Okay? And get this Fermi surface. Can it exist in a purely two-dimensional system? Okay. So why not? Huh? That's right, but it can exist from a Dirac cone, but not in purely two dimensions. It can only exist at the edge of a three-dimensional thing. Let's see why. So I'm going to do 2 dimensions, so we're not going to try to find Nielsen-Diomia theorems in 2 dimensions. 2 dimension with time reversal. T squared equals -1. I've jumped to time reversal. How many, in a purely two-dimensional lattice, I have how many time reversal invariant points? 4. 1, 2, 3, 4. Okay? On every line that you go from here to here, these points have Kramer's degeneracy. There's a doublet here, there's a doublet here. Let's just draw this line. This is Kx. Okay? I have a doublet here, 0, and Kx equals pi. At Ky equals 0, I have a doublet here. So bands have to do something like this. Okay? Just drawing them, just kind of artistic, or not lack of artistic. Okay? But they have to do this. How many Fermi surfaces would I get if I would just put your Fermi level anywhere? Sorry? 4 points, right? How many surfaces, how many Fermi surfaces has this one? There was just one here. How many, say, take kx equals 0. How many has it got? 2 points. Okay, there's a problem. Anywhere I put it, I would get 4 points. I can just tune the Fermi level, whatever you want to. Same thing here, okay? So for example, if I put my Fermi level here, such a surface, if somehow I shift my 2D band structure to have the Fermi level here, if it's purely 2D, if this is the pi point, there have to be 2 Fermi surfaces here, right? It's just the same thing as this, as the 1D. In 1D, you cannot have an odd number of helical pairs. In 2D, you cannot have an odd number of, what are these two, how do you, what's the Hamiltonian here? Around these points. What's the Hamiltonian here? For very small. What is it? So I have delta kx and delta ky, and I have 2 bands. So what's the Hamiltonian? Okay? And this is the Hamiltonian with some coefficients around every one of these points. So how many do I have to have in a purely two-dimensional lattice? How many? These we're going to call them 2D Dirac Fermions. Okay? These are called 2D Dirac Fermions. And the reason why I don't call them Weyl is because in 2 dimensions, this is the lowest dimension of fermions that you can have. You cannot decompose this into 2 more. Okay? Well, this is just, in 2 dimensions, basically, you call them Dirac because this is the Clifford algebra. The Pauli matrix of a Clifford algebra in 2 dimensions. We can get back to that. But the point is, I need to have, in every 2D lattice, I need to have at least 4 Dirac fermions at the 4 time reversal invariant points. Okay? So, and anywhere I put my Fermi level, you can think of this as rotating this in the y direction to make it, you know. Everywhere I put that damn thing, you know, I can give you a Hamiltonian which is fully periodic on the lattice, which has 4 sine kx sigma x plus sine ky sigma y. Okay? This is a purely time reversal invariant Hamiltonian because this is spin. Time reversal flips it. Time reversal also flips the momentum. It's time reversal invariant. It has degeneracy points here, 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 Kramer's degeneracy. And around those points, the Hamiltonian looks very much like this with different coefficients. Okay? So, on every lattice, I need to have 4 of these if I have time reversal. Okay? If I have time reversal, I need to have 4 of these. So, if I have 3 or 2 or 1 of these, I cannot realize them in 2 dimensions purely. And those correspond to being the edge of a weak topological insulator or a strong topological insulator, or a weak plus a strong topological insulator. So let's see how that goes. So Nielsen-Niamiya tells you that you must have 4 Dirac fermions in 2 dimensions. Okay? So if I have 1, okay, if my Fermi surface looks like this, okay, if I have 1 Fermi surface, okay, clearly it violates this. I cannot do it in 2 dimensions just by drawing it. You can clearly see it. And you know that this is the surface of a 3-dimensional Fermi surface of a 3-dimensional topological insulator, right? In the gap. When I move the Fermi level lower, this Fermi surface shrinks, and there's a Dirac node here, which is protected by time reversal. Of course, the way you go around the Nielsen-Niamiya is you don't really have just 2 dimensions. Again, the spectral flow to a bulk state and the system is fully periodic, but you need to go from the surface to the bulk. Okay, so this is, okay, and then the bulk states are here, and there's another Dirac cone on the other one. Does that make sense? Any questions? Simple? Too simple? Yes? Well, basically, you see, like, as you noticed here, when you cut this, you have 4 points. So really, any Fermi surface that's two-dimensional has to look like this. It's purely two-dimensional, right? If I make a cut, like this is one, this is, you know, I can, this is at k, this is kx at ky equals to 0. I can move a little bit away from ky, and I just rotate this, and it has to look like this. I have to have 4 points. Okay? What that corresponds to is kind of taking this guy, moving it on the upper surface, and taking this guy and moving it on the lower surface, roughly, not particularly. But the point is, what I want to make clear that's understood is that you cannot have this in 2 dimensions by itself. If you can't have it in 2 dimensions, but you're perfectly able at drawing, you know, I could perfectly be able to draw in every, this is a function of momentum. In every momentum, I'm able to draw this band structure that now goes through some states here. It's periodic if I include a bulk, okay? Then that has to be the edge of something, right? Okay, so now, can I have the following situation? In 2 dimensions. Can I have these 2 Fermi surfaces in 2 dimensions? What do you think? Right, I mean, that's right. So this situation, what I would claim is that you can take this situation, change the Fermi level, move it to have something like this. Of course, this follows here. Move it to have something like this. This follows here. Okay? At some point they touch. There's nothing that prevents hybridization between them. They'll do this. In time reversal invariant fashion. Now, what's the Fermi surface of this? What does this remind you of from like what you saw in Binghai's talk? This is a weak topological insulator in 3 dimensions. This is the surface of a weak topological insulator in 3 dimensions. So for example, if I look at kx, this is ky, this is kx. If I look at kx equals to 0, ky equals to 0, right? How many Fermi points have I got? 2, right? But I know, if I think of ky as a parameter, right? I know that ky equals to 0 is a time reversal invariant momentum. So as a function of kx, at ky equals to 0, my system is time reversal invariant just as a function of kx. Of course, if I move to different ky, I have to change ky when I apply time reversal. But if ky is equal to 0, this system here has to be time reversal invariant by itself. Okay? So I can think of this as a 1D Hamiltonian with time reversal invariance. But this 1D Hamiltonian would have 2 Fermi points. But we just proved that you cannot have a 1D Hamiltonian with 2 Fermi points with time reversal invariance, right? Then we just proved this, right? This is a 1D Hamiltonian. We can't have 2, right? So this has to be the edge of something also. And the way you see that it's a weak topological insulator is that you can kind of see that I can make changes in the Fermi surface, in the surface Fermi surface, such that the Fermi surfaces look like this. You can mess around with the parameters, just tighten up the bondings, do like things that non-universal things. Fermi surfaces start looking like this. This is just flat Fermi surfaces with no hopping in the y direction, right? So this is just stacked. This is for every y. This is the Fermi surface of an edge of a 2D top. So this is 2D quantum spin Hall, 2D quantum spin Hall. This has a Fermi surface on the edge. So this direction, periodic boundary condition, Kx. This direction, periodic boundary conditions, Ky. This direction, open boundary conditions. So I have a surface. This has 2 Fermi points. You can clearly see them. This has 2 Fermi points, 2 Fermi points. The Fourier transform just becomes a stacking. Yeah? So maybe this is a good time to take a quick break and answer questions. So something is unclear. I can see from people. I mean, so what's unclear? So it's bad if I haven't been able to even convey things that. Well, what's unclear? So could you just tell me if it's clear or not? If it's right. So I asked, can you have this type of a Fermi surface in just purely 2 dimensions? Just purely 2 dimensions. And I've argued that you cannot. So is it clear that you cannot have just one of them in purely 2 dimensions? Right. So now I'm arguing that you can understand. So this was kind of clear from, but I'm arguing you can understand weak topological insulators also by breaking. So the Nielsen-Miyamiya theorem will tell you that in a purely two-dimensional surface with time reversal invariance, you need to have 4 Dirac Fermions, one of them at each time reversal invariant point. If I have this guy, like this, then this would tell me that if this Fermi surface has to do something if I change the Fermi level. I would shrink it or something. So this guy, here is the time reversal invariant point, here is the time reversal invariant point. So at some point, I would just have 2 Dirac nodes. It would violate this. So I know this can't exist in purely 2 dimensions. So I'm going to try to understand what does it represent the edge of. I know it's got to be the edge of something. It can't exist in purely 2 dimensions. I don't have to go to 3 dimensions. Okay? So now I'm going to go to 3 dimensions and think of this Fermi surface, of this situation, as the Fermi surface of the surface state. That's all what we've been doing. We go to 1 higher dimension. We think of the remnant Fermi surface that we said cannot exist in just purely 2 dimensions. We think of it as the projection of the 3rd dimension. Make sense? So I've argued that I can just change the parameters. I can just work with a surface Hamiltonian. There are several things I cannot do to work with a surface. I can't get rid of this guy just by working with a surface Hamiltonian, because getting rid of this guy is never, if you tune the Fermi level, it's got a point, and that point moves back. So you can never get rid of this Fermi surface. If you got rid of the Fermi surface, I would move to this topological class, which we know, if I got rid of one of the Fermi surfaces, I'll move to this one, which it's a different topological insulator. So there's got to be a bulk phase transition. I can't get rid, but I can change parameters in them. So I'm going to change the parameters in this way. I'm going to make this surface bigger, and at one point, they'll touch. Right? I'm going to hybridize them. And then at one point, these are Fermi surfaces that are distinct by Lifshitz transition between one from another, but topologically, they're the surface of the same topological insulator. Once I've done this, I'm going to play around with the surface hoppings a bit more, so I make this exactly flat. That corresponds to no hopping in this direction, right? Because if there was hopping, I would have some dispersion. So this I can interpret as a stacked 2D topological insulator in this direction, right? So this is my handwriting blows, but I should think, right? You should think of this. This is Kx, this is Ky. If there's no hopping, I can Fourier transform or not Fourier transform. I don't care, right? So a 2D topological insulator has as edge modes, so the topological insulator is in this direction, has as edge modes 2 points. You can see them. And I'm just stacking them in the y direction. So this is a weak TI. Okay? And the fact that it's a weak TI, you can also see it because you got a preferred direction in this system. This system had no preferred direction. If you just have one Dirac cone, it's got no preferred direction. Okay, it sits somewhere. But this system has a preferred direction, and that's the distance between the two nodes, right? In this direction, I've stacked my system in the y direction. Right? You can clearly see it's got a preferred direction. So this is just a weak topological insulator. Okay? Can I have this on the surface of a 2D, or can I have this in a purely 2D system? Same thing, yes. It's like, isn't it 1 hour and 45 minutes?
I was programmed to send questions for myself.
Ah, okay. Oh, okay, I thought it was 1 hour and 45 minutes. Okay.
No.
It's a German quote. Let's go.
So we only
Okay, good. Yeah.
But maybe, I mean,
Yeah, no, it's good. For me, it's I actually like just one minute more. Sorry, I think it's almost done. Well, this part. Okay. So I can't have this in 2 dimensions, and you can clearly see that this is a strong topological insulator, but also a weak one, right? You can clearly see that this is also, right, I have weak indices and strong indices. Okay. The other thing that I wanted to point out now is that this guy here, on the surface, I have a Dirac cone, and the density of states, I think this was pointed out by Binghai, density of states here is k dk over dk, because the energy is k. So this is varies as k. It's got 0 density of states. So if you actually try to do, to add in interactions to this one-body model, you will see that you need a finite strength of interactions to open a gap, and you can open a gap by magnetizing the system. If I have this Fermi surface is just this, I can open a gap by magnetizing the system, but magnetizing the system would break time reversal. So, okay, so in the next lecture, what I want to do is I want to I want to go to the graphene example and ask if there's any further protection of Dirac nodes in 2 dimensions away from time reversal invariant points. So time reversal invariant points, time reversal invariance is the only thing that's needed. Away from time reversal invariant points, whether you can have semimetals. And graphene is an example, so we'll understand that through group theory. So thanks.
questions are supposed to be answered on the bottom, right?
Yeah, I guess.
What do you mean with reconstruct?
Sorry.
What do you mean when you say the reconstruct is?
Well, so this guy has a weak index, for example, right? This guy doesn't have a strong index. This is not a strong topological insulator. The weak topological insulators are defined as stacking.
Yeah, exactly.
Right?
Did you say, okay, this is weak index, what, where is it?
So the weak index just tells you, the weak index is, so you know it's got an index, you know it's not strong, and there's only strong and weak indexes, so it's got to have a weak index. So what you do is, this is kind of like, right, this is a projection, there's a whole other dimension in this direction. And there's a whole other dimension in this direction, but I can always Fourier transform in that direction also. This is open boundary conditions. I can close my boundary conditions in that direction. I'm going to close my boundary conditions, and let's say I have inversion symmetry in my system, just to make it easier. You take the product of the inversion eigenvalues of the 2 points that project onto this point, and there's 2 points in the bulk that project onto this point on the surface, or onto this point. This is 0, 0, 0, and 0, 0 pi, 2 time reversal invariant, or inversion. The inversion eigenvalues, there's a theorem that you have to switch every time you cross a Fermi surface, you switch your inversion eigenvalues. So, they can be minus here, I switch across one Fermi surface plus here, cross no Fermi surface plus here, and go in this direction, cross another Fermi surface minus here. Here, going from, you see it's consistent, because here I cross 2. Okay? So the index is just when you see these tables of the inversion eigenvalues, that's what it is. And the rule of thumb is just count the number of crossings that